Alright, so I'm going to try to go through this in a way that doesn't take 6 minutes, and without saying 100 times. So, let's see. The given was this circuit. We need to find the voltage across this element right here. So I put A and B, just pretended that this element didn't exist. Started applying Thevenin's theorem, plus turning off the sources. With the sources off, I looked at this, realized those were in series, added them together, got 20 ohms, realized these are in parallel, did 20 times 5 over 20 plus 5, which equals 4, and then I added this 1 ohm, which was then in series with it, and got a Thevenin resistance of 5 ohms. Now for the voltage. For the Thevenin voltage, I marked these. Everyone uses kind of a different thing, so I was like, okay, I'm going to mark this D and this C. I sometimes use capital A and capital B, but I mix them up with these guys sometimes, so I'm like, okay, I'm not going to do that. So starting with this, I realized that I might as well mark this I1, even though I know I1 is 3 amps. Sketched in I2, I3, I4, and I5, even though I5 is not going to be anything, but I just did it just to help me manage what I'm keeping track of here. And I believe I did the calculations for this on the next page. So let's see, 3 amps, get it here somewhere. Yep, 3 amps equals I3 plus I2. Kind of broke that down, VD minus VC over 4 plus VD minus 0 over 16, because my reference node is 0 on the bottom, and that's heading towards that. And I got one equation. I realized I probably am going to need 2, so I moved on to the next node, which is the node whose voltage is going to help represent our Thevenin voltage across the circuit. So I did I3 equals I4 plus I5. Can't see my mouse at all. I3, I4, I5. Let's see. I3. I4, I5, and so I think I'm just assuming that I5 is 0, but I'm still putting it in the calculations just to keep everything organized nice. Yeah, there we go. So I marked that as 0. Still carried it down for some reason, just because I like keeping things organized. So VD minus VC divided by 4 equals, and these are of course the Ohm's law representations of my I3 and I4 currents. Where are we at? 2 minutes 50 seconds. Alright, so now that I have my 2 equations, I'm like, okay, I've got 2 equations and I've got 2 variables, so I can just pop this into my calculator under the system of equations linear solve. And I've been doing that a little bit more lately. At first I was just doing all the algebra, but I realized I was literally spending, so I did this here just to show. You can just do it on the calculator, or I can just do this by simplifying, but I've realized that this process takes me 70% of the time. So the first, getting to this point where I'm popping the numbers into the calculator took, I don't know, however long that took, 5-10 minutes, and then when I do the algebra, it's like another 10-15 minutes sometimes, because I almost always get a mistake with the symbol. So I went through this and I got some silly number, and I'm like, well, what's wrong? And then I backtracked and realized I forgot a minus or accidentally multiplied this by something. I don't remember, but I had to go through it, which wasted more time. So, but I did it anyways, just to show that I know how to do the algebra or whatever. And so I got the same number, 19.2, as the calculator gave me, with the system of equations linear solve, which is 19.2. And so now that I have my Thevenin voltage, hopefully I marked it as that, well, maybe not quite yet, but I popped my Thevenin voltage in with my Thevenin resistance, did a voltage division, or not voltage division, did the ohms thing that I can't remember the name of right now, Jesus. Resistance division, I don't remember right now what it's called, but anyways, I did that. Normally I know that you can do it with the 19.2 times with the 10 on the top to get this number quicker, but I like doing it like this just so I can like visualize things better, and it's good practice for me. So I calculated the voltage across this and then subtract that from this to get the voltage across this, voltage difference across that. Oh, look at that, almost 6 minutes. Well, I'm just going to go for it, I guess. I just kind of wanted to backtrack to this, where I proved this, because I was thinking, I'm like, something that probably catches a lot of people up is it's like, okay, at node D, the difference between node D to, I guess, node lowercase b or whatever, terminal B, the difference is 24.96, and I was thinking, I'm like, well, maybe people that have trouble visualizing that, what they should be looking for is the difference from here to here, which is the same as the difference from here to here, since that resistor's chilling out in limbo. It's applied in whatever way the difference between the voltages from the left side of it or the right side of it or whatever is going to be the same. I was thinking, I'm like, yeah, maybe people would find it helpful for visualizing why node C's voltage difference is the one you're going to use for your Thevenin voltage versus node D. And I was just thinking, it's interesting because, yeah, I mean, I guess if your terminal B was like over there or something, it would be a different circumstance, but since it's over here, it's going to play out the way that it did anyways. I'm just going to stop this.